yeah, I put this link on under chat box there, so you guys can. I also have this on the website. This is I want to go over the calendar, the remaining grades in this course over these next 3 weeks. All right, so I've tried to update all the grades up to this point, so everything in the grade book should be current. I know there are some students who are missing or I'm missing some assignments as far as the previous homework assignments go. So if you see some ones in the grade book, that's why, because maybe I'm missing assignments 5 through 7 or missing 8 through 9. If that's the case, you can always finish those assignments up, send it to me through email, and I'll be able to update your grade up to an A, assuming that everything is there that you've completed. So the Friday before the break, we started a new set of assignments, and now these new sets of assignments will go as test grade under the pre-AP test categories. So we're going to finish up on differential equations and volume FRQ worksheet today that we didn't get to finish the Friday before break. And then we'll move on to particle motion and Riemann sums FRQs. And this will be day 1 of 2. So we'll spend 2 days over this. But each day there's going to be assignments associated. And so every day I'm looking at 4 pages for you to turn in. Okay. And they're going to be due each of the Wednesdays starting next week. Okay. So Wednesday we'll do antiderivative word problems worksheet. Thursday we'll do differential equations. We're kind of just hitting, reviewing these big FRQ topics, and then Friday we'll do test review. Your test is going to be just over 2 FRQs, and it'll be front and back of a sheet, so it'll be pretty much the same length as your previous FRQ quiz that you took, but it's just now going as a test grade, and it'll be over these 2 topics. Okay, so after we get done with that, then we'll move into multiple choice preparation. So we're also going to take a multiple choice test. This is, in the past, I've done a full mock AP exam, but this is the condensed version of it because of the time and just because of the way that we're kind of spread out between face-to-face and virtual. So we'll spend 3 days or 4 days going over some multiple choice topics, and I'm going to try to cram in as many different topics as I can. So over the course of 16 multiple choice, I'm going to try to hit what I identify as the 16 biggest topics of AP exam. And so if you want to look at that list, you can go to my website and see the topics that I listed out. It doesn't mean that I'm going to cover all those topics, but I'm going to try to pick problems on each of these worksheets that kind of hit on these topics, so you can kind of get more comfortable with the different variety of problems that we can see over the course of an AP exam. And then that'll be worth 50 points, 16 multiple choice. So that's going to comprise 100-point test grade. And then I'm going to try to do some miscellaneous last-minute topics, either more obscure topics that we haven't seen, or just kind of reviewing on ones that we hit from before. Monday before your exam, I'll go over tips, I'll go over formulas, and I'll go over some last-minute review. Your exam is going to be in the gym, 8 to 12 a.m., I believe is the time. Okay, and that will, yeah, I don't really have anything to do for us after this date, except for maybe working with students who need to bring up their grade up to passing. So I may be working with more individual students after this date. But you're going to be turning in these assignments over the course of these next 3 weeks. So the first homework assignment is going to be due not this Wednesday, but next Wednesday. So assignments 1 through 5. starting with the assignment from the Friday before break up until Thursday. That's assignment number 5. And then 6 through 10 is going to be due the following Wednesday evening before midnight. And then finally, the day after the AP exam, you'll turn in assignments 11 through 16. Okay. The hope is that now all this is going to go in as one test grade, a 200-point test grade. 100 points should be guaranteed, assuming that you do all your work and you turn everything in. And then the other 100 points is going to be made up of the FRQ and the test. So think of the homework assignment is kind of like a curve on top of this portion of your test grade, of your quote unquote exam grade, but I'm just including this as a test grade. Okay, any questions that you guys have about these remaining weeks? Okay. All right, so I want us to finish up on the handout that we started the Friday before break, differential equations and area volume. We did the first page, differential equations. We did part of the second page with washer method. So now let's do another washer method problem with number 3 here. Okay, so it says let R be the shaded region bounded by the graph y equals natural log of x and the line y equals x minus 2. Find the area of region R. So area is just top minus bottom or right minus left. But since everything is given to us as y equals, then it's just going to be easier just to do top minus bottom. So let's just do top minus bottom here. Area is just the integral from left bound to right bound of top graph minus bottom graph. There's no pi, there's no squared. Okay, it's just going to be simple area here. Okay, so the top graph being the curve, the natural log of x, the bottom graph being the x minus 2. Make sure you have a set of parentheses as to protect the multiple terms that are in the bottom portion here. But we still need the bounds, right? We need the left bound to right bound. So we need to use our calculator and graph our graph and look for the intersection. Second trace intersect, or you can use your 36 Pro and find the use numsolve to find those intersections of the x values. Okay, so I'm going to write the full order pair here. We may need the y value later, but right now we only need the x. Okay, so we have our left bound to right bound in terms of x. So we're starting at 0.158 and we're extending to 3.146. Okay, the rest goes in our calculator. Okay, part B, find the volume of the solid generated when region R is rotated about the horizontal line, y equals -3. So we see that this is the bottom of this graph is at -1.8. So we know -3 is going to be somewhere further below that point. So we're expecting a washer method, right? There's a gap. We need to draw 2 radius. So I'm going to put the diagram here. I'm going to save this diagram for part C here. So we're extending from the axis to the furthest boundary of our shaded region. That's big R. And little radius from the axis to the closer of the 2 boundaries. Okay, big R and little r. Okay, let's find the expressions associated with each of the radius. Big R is just top minus bottom. Top is sitting at the natural log. The bottom is sitting at the -3. Okay, little radius is x minus 2 minus the -3. I think we're ready for our volume formula for washer method. Bounds in terms of x, big radius squared minus little radius squared. We use the same bounds as before. Remember that your bounds are only for your shaded region. So if we're talking about the same shaded region for area, for volume, for disk, for washer, if it's all from the same stem problem, our bounds will not change. So it doesn't matter where your axis is, it's going to be the same boundary. Okay. Assuming that we're still doing top minus bottom, which we are. Okay, big radius, clean this up. 2 negatives become positive. Minus little radius squared. Next, this becomes -2 plus 3, which is 1. The rest goes in our calculator. Or you can multiply that pi through. Okay, any questions there for A or B? All right, part C, find the volume of the solid generated when region R is rotated about the line x equals -1. So I'm going to use this diagram for this. This is going to be a vertical axis of revolution. I'll put this over here. We see that there's still a gap between the axis and the shaded region. We know this is going to be washer method. We go ahead and draw our 2 radius, extending from the axis to the furthest boundary that we see, and then from the axis to the closer of the 2 boundaries. But anytime you see a horizontal radius, that should be a red flag, because that means we most likely will have some additional work in terms of setup. What I mean by that is, if we do right minus left, these equations that's given to us is not in the proper form. We have to rewrite them as x equals. Everything has to be in terms of y. So if we're dealing with top minus bottom, this is perfect. But with the right minus left, everything that's inserted has to be in terms of y. So to ensure that, we get x equals, so we can isolate the x on one side and everything is in the perfect form to be able to plug in. Also, our bounds need to be adjusted. It needs to go from y1 to y2, lowest to highest y value instead of left to right x values. So we need to make some adjustments with these equations here. Y equals natural log of x needs to be rewritten so that we can solve for x. The way we get rid of natural log is we involve its inverse, which is base e. We know e and natural log will cancel out, leaving me with x equals e to the y. So this is my adjusted equation. Now that's going to represent the curve. And then initially I had y equals x minus 2. If I solve for x, I get x equals y plus 2. And now this is my adjusted equation for my linear graph. So washer method again. R of y. Right minus left, we look at the big radius here. So it's going to be y plus 2, which is the right endpoint, minus a negative 1. And we also have little radius, which is right minus left, the e to the y minus a negative 1 here. So here's our volume formula. From lowest to highest y value, we need to make that adjustment because of right minus left of our radius. So now these y values will come into play from our bounds. Lowest, our bounds will now be in terms of y, lowest to highest. Okay, so big radius squared minus little radius squared multiply that pi through. Either form is fine. Okay, just wanted to finish up this review of volume. Any questions here? Okay, let's look at today's worksheet. Particle motion and Riemann sums. These two topics are not necessarily always overlapping, but I picked ones where they did overlap so we can kind of explore both of these topics within a problem. So, but let me review a little bit of particle motion. Yeah, just some of the formulas that we're going to potentially need, or also some connected information that is good to know. Particle motion, I think we understand velocity, acceleration, and position, and just their relationship with each other from a derivative perspective. I think we're pretty comfortable with that. We know position's derivative is going to be velocity. Velocity's derivative is going to be acceleration, and that's demonstrated here. So I think going down that pathway is pretty straightforward for us, but I think we also need to be aware of understanding how to go up that chain, right? How do we get from acceleration back up to velocity? How do we get from velocity back up to position? And the way we do it is we go through antiderivative, right? It's in that word, anti-differentiation. We're doing the opposite procedure of differentiation, of derivative. So if we're starting down at the acceleration level, if we take the antiderivative of acceleration, it's going to bring us up to the velocity level. And if we take the antiderivative of velocity, it's going to bring us up to position level. But if we just take the integral of velocity, it'll give us the change in position, displacement, but it won't give us distance. Okay? Distance will require absolute value of velocity. So just to kind of give a quick visual perspective here, if I have a velocity function and this chart represents either above where he's moving to the right or below where he's moving to the left, we can think of it as the areas inside these regions indicate how far they traveled and in which direction. So let's say there was a -5 here. Let's say this was 3 and this was -1. That means he's moving 5 units to the left, stops, turns around, 3 units right, stops, turns around, 1 unit left. So displacement is just the integral of velocity. That means I'm just going to total these up, keeping track of the signs. So -5 plus 3 is -2, -2 minus 1 is -3. That means from where he started, he's going to, this object or this particle is going to end up 3 units to the left of where he started. Okay. But distance is where we take from A to B of the absolute value of V of t. So the total distance achieved by this object is 5 plus 3 plus 1, which is 9. So through all the forwards and backwards motion, he's going to travel a total of 9 units, but his displacement is -3. All right, so understand that distinction and the absolute value and without the absolute value is what's causing that distinction. Average velocity is, if we're given the velocity function, if we're asked to find the average velocity, we take the integral divided by the width. It's basically a reworking of the area formula of a rectangle. So this is basically average value theorem. But sometimes you're also asked to find the average velocity given the position function, which is just basically the slope of the position function. So these look very different from each other, but they actually are the same thing. It's just we're starting at a different point. If you think about integral of velocity is just position. So using first theorem, you know velocity is going to turn to x of b minus x of a. So this portion becomes x of b minus x of a. And if you look, it ends up giving us the same value, even though we're starting at a different spot. Average acceleration is just change in velocity over change in time. Just the slope of your velocity function. Displacement of position, these are both just applications of first theorem. We know the integral of velocity is going to move up to position. We know the integral of acceleration will move up to velocity, and that's just plug in the bounds if they're available for us to plug in. So this will give us the change in position over the 2 time periods. This will give us the change in velocity over the 2 time periods. We've also seen this from before. This shows up, these types of problems shows up in particle motion as well, where I'm looking for a final position, I'm giving an initial, and I need to tack on the displacement or the progress made between the 2 points. Increasing speed, decreasing speed, this is a more first semester review. If I want to find increasing speed or decreasing speed, I got to compare signs between velocity and acceleration. Same signs means increasing speed. Opposite signs means decreasing speed. Increasing, decreasing velocity, we look at the acceleration. So I think this is where we may get thrown off because of the word velocity. But notice that if I just have velocity, then yeah, we can rely on velocity. But the fact that we're saying increasing or decreasing, it changes the meaning. It changes what we're asking to find. So increasing velocity is really referring to rate of change of velocity, which is acceleration. So we only rely on acceleration and the signs of acceleration to determine if a particle is experiencing increasing velocity or decreasing velocity. Okay, so let's see if we can apply some of these formulas into this problem here. So a car travels on a straight track. During time interval from 0 to 60 seconds, the car's velocity is measured in feet per second. Acceleration is measured in feet per second per second. They're both continuous functions. No breaks in the graph. Table shows selected values. Using approximate units, explain the meaning of the definite integral from 30 to 60 of the absolute value of v of t in terms of the car's motion. Well, we know the absolute value of v of t is going to refer to total distance, so we can include that in our explanation. Okay, total distance traveled between the two time periods, between 30 to 60 seconds. Approximate using trapezoid approximation with 3 subintervals. So as a reminder, area formula for a trapezoid is 1/2 times width, and then height 1 plus height 2. Okay, we're looking at that interval from 30 to 60, so we can indicate them with brackets to help us find the width of each of the subintervals. 30 to 35, that's a width of 5. Here, that's a width of 15. And finally, width of 10. Hey, width component, 5. And then I got to add up the heights. You got to be careful here, though. We're talking about absolute value. So just like how we talked about before, how all these regions need to be adapted to be positive for us to get that true read of distance. So that means we have to adjust these as well. These negative need to be converted to be positive. So width is 5 and my height is 14 and 10 for my first trapezoid. Okay, 1/2 width, height 1 plus height 2, and then 1/2 width. Add all that up, that ends up giving us 185 feet. Part B, using appropriate units, explain the meaning of the integral from 0 to 30 of a of t in terms of the car's motion. Well, we know what happens with a of t. We know the integral is going to move it up to velocity, and we can use this formula here, right? Integral of a of t becomes v of b minus v of a after we enter in the bounds. Oops, a. So I think we have a much easier time interpreting what this means, right? This is just saying velocity at 30 seconds, velocity at 0 seconds, and then we're just finding the difference between those two. So we're just finding the change in velocity, comparing the velocity at 30 seconds versus the velocity at 0 seconds. Okay, so we're asked to find the exact value. So now that we're sitting at velocity, we can pull that information, right? Velocity at 30 seconds, velocity at 0 seconds. I'm just finding the difference between these two values. So that's basically positive 20 minus 14, which is 6. So we know that over the these two time periods, the velocity is going to increase a change with 6 feet per second between 0 to 30 seconds. Okay, part C, between 0 and 60, is there a time such that v of t equals -5? Can we guarantee a velocity of -5 somewhere in this time interval? So if we look at our velocity function, looks like we can see what's happening, right? -20 goes down to -30, goes up to -20, goes up to -14, and eventually hits 0. So somewhere in this time interval, it's got to cross -5 somewhere between, right? We're told that these are continuous functions. So it's got to cross through somewhere between at least once. Maybe there's more than that, but with this data, we can't guarantee that until we see this, right? So this is basically an application of IVT. Intermediate value theorem says if I'm trying to guarantee a value, as long as there's a value below and a value above and the graph is continuous, it's got to cross through that target somewhere between. So we can say by IVT, since the velocity at 35 seconds is -10, and -10 is less than my target, and then I know it's also less than my other endpoint, which is 0, which is occurring at 50 seconds, then there must be a time in the time interval from 35 to 50 such that so all I'm saying is I'm guaranteeing that value of -5 because I'm starting below -5 and I'm ending above -5, so it has to cross through -5 somewhere in between. It's an easy, I think IVT is a pretty easy concept, but it's a little cumbersome in the way that it's written. So this is the way that that they're suggesting to write it. So this way you can be guaranteed to earn the full credit points that they're asking, because they want students to be able to identify why they're getting those values, right? If you just say -10 is -5 is between -10 and 0, you're not really showing how you're getting those values. So if we indicate that you're pulling them from the table and you're indicating the time interval that's occurring, and you're also explicitly comparing and showing that IVT means that you're guaranteeing that value between two endpoints. So this is the suggested way of writing it. Right. I see some students, or they would take off points if you just say velocity is -10 and velocity is 0, so therefore -5 must exist. But you're not. But if you're not comparing it explicitly, you may not earn full credit points. So with IVT, I think this is the best way to efficiently earn the points that you want to earn. Okay, any questions there with part C? All right, last part here. Between 0 and 60, is there a time such that acceleration is 0? So I think the first instinct is you look at the acceleration table and you say, well, I don't see any negatives or I don't see any zeros. So I can't use IVT. So it looks like I can't guarantee that acceleration being 0. So this is not going to be IVT problem because we actually have velocity to help us out with that process. So to kind of give you a visual as to what we can do here, think about what acceleration equals 0 mean. Acceleration equals 0 means, can we guarantee that the slope of the velocity is ever going to be 0? Okay. And if we can kind of visualize this graph, we can decide whether we can guarantee that or not, right? So we're starting at -20. So the velocity starts off at -20. It goes down to -30, but then it comes back up to -20. So we don't know exactly where it's going to come back up, but it has to come back up, right? It's a continuous function. Acceleration is existing, so we know it's going to be a smooth curve. And if the graph is starting at -20 and it goes down and comes back up again, there must be a place where the slope is 0. And slope of velocity is acceleration. So based off of this, we can guarantee, right, that there must be a place. It may not occur at 15, but it's got to occur somewhere between 0 and 25, right? It's got to come back up somewhere between. And through that coming back up, there has to be a slope 0. So this is an application of Rolle's theorem. Rolle's theorem says, as long as my endpoints are the same, I can draw a horizontal line between the two endpoints, which means that there must be a place of a horizontal slope somewhere along that curve. Okay, so we can write it this way here. By Rolle's theorem, since velocity is continuous on the closed and differentiable on the open, and I identified two endpoints with the exact same velocity, it's got to go down and come back up, or go up, come back down. Along that process, I have to have a slope 0 somewhere along that curve. Okay, let's see if we can make some progress with the problem on the back of this worksheet. Okay, so another table of values here. Temperature of water in a tub at time t is modeled by a strictly increasing twice differentiable function. Increasing, it's always rising. Differentiable just means the smooth curve. With Wt measured in degrees Fahrenheit and T measured in T minutes. At time T equals 0, temperature of the water is 55 degrees, so that's the starting temperature that's given to us. Water is heated for 30 minutes, beginning at time T equals 0, but we're only given information for the first 20 minutes on the table. Part A, use the data in the table to estimate W prime of 12. Let's talk about what W prime means. So W prime is just the rate of change of temperature with respect to time. So we're not going to be able to know the exact rate of change at 12 because we're not given that data, and we don't have a formula that we can find the derivative. So the best we can do is just pick the two closest points, and it's an approximation, but we know that the closer that we are to our source, the better our approximation is. So we can just do change in temperature over change in time using the data right there. Use our calculator, we get 1.107 degrees Fahrenheit per minute. So what that means is the temperature of the water is increasing at a rate of 1 degrees Fahrenheit or 1 degrees at that moment in time. Right, part B, use the data to evaluate the integral of w prime of t. So this one, we're not going to be able to use rectangles because we don't have w prime showing in the table. We have w of t, so what if we can find a way to convert this into w of t, and then we can use the table here. So we can apply first theorem. We know w prime after the integral process is going to push that up to the w of t level. Antiderivative of w prime is going to bring me up to a w of t level, and I can plug in my upper and lower bounds. So this is the water temperature at the 20th minute. This is the water temperature at initially. So we're simply finding the difference between the change in temperature between 0 and 20 minutes. Okay. Now we can use our table of values. W of 20 is 71 degrees. W of 0 is 55 degrees, and we just subtract those values. Okay, let's do one more section here, part C. Between 0 and 20, the average temperature is given by this average value theorem here. Use a left Riemann sum. Okay, so now we can use left Riemann sum because we actually have W of t to read off of with 4 subintervals. I'll push the 1 over 20 out in front, and then I'm going to use Riemann sums to approximate the area under that W of t graph. Okay, so 4 subintervals here. Left Riemann sum, I know I need width and height components, so if I subtract the t values, I get the width. Okay, so now we just go through the process of width times height, width times height, width times height, and width times height. Okay, we total that together, and it's going to come out to be an average temperature of 60.79 degrees Fahrenheit. It's asking also, is this approximation going to overestimate or underestimate the average temperature? So the way that we can tell is, let's sketch out the graph, right? We know that this curve is always increasing. So imagine a graph that's always increasing. But the way that you draw your rectangles is that you're always attaching the left endpoint of every rectangle to the graph. And when you do that, you convince yourself that all these rectangles are going to sit nicely below the curve. It's going to be an inscribed rectangles, which means that all these area of the rectangles is going to be less than the actual area because we see all these gaps below the curve. So this estimation will under approximate since we're using left Riemann sum and an increasing graph. So a lot of times we just have to sketch something out and just convince ourselves whether we see the geometric shape below the curve or above the curve. If it's above the curve, it's an overestimation. Below the curve, it's going to be underestimation. Okay, we'll finish up with part D tomorrow, and we'll also continue to day 2 of particle motion and Riemann sums. But hope you guys have a great day. I'll see you guys tomorrow. Thanks, everyone.
Thank you.
Thank you. Have a good day.